Hi, everyone, and we're going to have the second lecture this morning. And Professor Carlo Marinelli will continue on the topic analytic inequalities. Carlo, please. I cannot hear your voice. I'm not sure if
Is it okay now?
Yes, it's right.
Yeah.
It's okay now. Yeah.
All right, sorry.
Thanks.
So I just recalled here the formulation of the Cauchy inequality for sequences, as we know that we had also a slightly more abstract formulation written in these terms. And yesterday I sketched a proof of the fact that by suitably iterating this argument, so by starting like a sum, let's say, of AI, BI, CI, DI, and then so this would lead, for instance, to something like AL4, BL4, CL4, DL4. Remember that we use this as notation only because we don't know that we don't know yet that it is a norm. We only showed it in the case L2. So remember that, maybe just so that if we have a sequence A, then by this LP we mean just this. So we always with our convention that we take positive only. So this is like that. Okay, and we do not know yet. We proved that it is a norm in the case of exponent 2, but we do not know whether it is also in the case of exponent p. So it is just terminology for the time being. So I claim that it will be possible to extend this to the case where you have 2 to the m elements here. So then you would have L to m, L to m, and so on with 2m members. Then one can pass to and this is the difficult part is to understand what happens if you have a number of elements here that are not a power of 2. That is also not particularly easy to come up with an idea to get that. As I said, because of lack of time, I want to do this proof, but I just give an idea of what happens, but I will write the whole proof in the notes. Then one manages to prove indeed that if you have, let's say, A1, now, as I said yesterday, I changed notation. Here, this means sum of AI1, A21, A1i, A2i, up to mi. So these are labels for the number of series that we have here, of sequences that we have here. Then we would end up with something like A1 up to AM. And here we would have LM. Furthermore, it is possible then to look at the case where we have exponents here, so we can move from this to this, then from this to another situation where we have A1 alpha 1 up to AM alpha m. And then here this would allow to get inequalities of the type actually sum of A1 to the power alpha 1 up to sum AM to the power alpha m. And the sums of the alpha 1 plus alpha m is equal to 1. So this can be shown that it can be, so in the case of rational, then in the case where alpha I, alpha m are not rational, we do another approximation by rational number. We use the continuity of the functions on both sides of the inequality. So this is the same idea of Cauchy essentially that we developed entirely, but the difference is that here, of course, one has to, so this step is the difficult step, passing from 2k num to 2k cardinality of the set to a cardinality of set M. So this is the, to a set of cardinality, I'm sorry. I switched the words. So this is the, let's say, not easy case. All the rest is, let's say, technical, but not too bad. And finally, we are able, by doing substitutions, I wrote this intermediary step because it is important to note that the sum of the exponents needs to be 1. So then switching essentially from alpha to 1 over alpha, this is what we will do here, we end up with the inequality that is most commonly called the Hölder's inequality, which is this. We have A1 LQ1 up to AM LQM, and the restriction is that the sum of 1 over, so the harmonic mean actually of this, well, similar to the harmonic mean but not quite, of this QM is 1. Okay, so this corresponds to this restriction on the exponent alpha. So as a matter of fact, these two last expressions are completely equivalent. The original derivation of Hölder's inequality first by Rogers, then by Hölder, was actually this form, and it is also written in older books in this form, while the, let's say, most commonly way of writing it in, let's say, more contemporary literature is this one. But the two expressions are really exactly the same. Okay, so this proof, as I said, is not a developed one, not a fully developed one. I just gave the main ideas, but I will give another proof that exploits another good friend of us, which is the AMGM inequality. So, and also another observation that we said that it is a very powerful one, which is homogeneity. So look first that, again, since the goal is to prove an inequality of this type, we made the observation already quite a few times that both the left-hand side and the right-hand side are separately homogeneous in each one of the arguments. So this, as we already did several times, implies that we can prove the inequality under the assumption that the norms, so that the norms of A1 LQ1 is equal to the norm of AM LQM, and they are all equal to 1. Okay, this corresponds, remember that this corresponds, so as I said already, if you believe that this argument is a little bit too magic, then the usual way to convince yourself is to replace I by a normalized version, which we call hat AI, which is just defined as AI divided by its norm. So this will be LQI. So you replace each of them by this way, and then you apply the inequality, and you see that it will be exactly the same. Okay, so where does the AMGM inequality come into play? It comes here into play. So we have that A1 AM. Clearly, this is something that definitely calls for being treated by the AMGM inequality. So since we want these exponents Q1 up to Qm to play a role, then and we also want to take advantage of the relation among the Q1, Qm, so that 1 over the sum of 1 over Qi is equal to 1. And then we make it appear exactly in a form which is suitable to be used within the standard formulation of the AMGM inequality. And the way is this. So first we do A1 Q1, and then this we write it 1 over Q1. So we have done absolutely nothing other than a rewriting, but this is the correct rewriting in order to use the AMGM inequality, because the sum of the exponent is less than 1. And what do we know about this? Well, the AMGM tells us this, that this is 1 or less or equal than exponent times the argument, so a1 q1 plus a 1 over qm am to the power qm. Okay, so then at this point, essentially I claim that the proof is over, because all we need to know, all we need to do is to sum on both sides. So we sum and we sum, so that the sum goes here and the sum goes here. Then what do we know about this object? Well, this is nothing else than a1 lq1 to the power q1, right? But this is 1. And the same applies to all other terms. Therefore, we have shown that this is less or equal than 1. I'm using the normalization hypothesis. 1 over q1 plus 1 over q2 plus 1 over qm, which is 1, which is exactly what we wanted to prove. Okay, so we have proved that this is bounded by 1. So this completes the proof of the Hölder's inequality. Okay, so as you see, the proof is very quick following this route. So it is a direct application of the AM-GM inequality. It is very convenient now to make an observation, and the observation is that we converted a pointwise inequality. So a pointwise in the sense that, maybe let us write it explicitly now. So we simply converted this fact a1i up to ami, so these are just numbers now, less or equal than 1 over q1 a1i plus 1 over qm mi. Okay, and all we did was to sum on both sides with respect to I. So that is why I say that we passed from a pointwise inequality, so in the sense that this holds for every I, to a global inequality, to a summed inequality. So this suggests that actually what properties are we using when we obtained this inequality? So we applied a certain operation on both sides. Okay, we applied an operation on both sides. With this operation, we can call it capital T, for instance. And then on these sides, what did we use? We used linearity. Actually, we used even slightly less than linearity. We used sub-additivity and homogeneity, and positive homogeneity. Right? So in the sense that if I apply T also on this side, so not what we are, maybe we let us keep note of what we are applying. So first thing, in order to claim that this is true, we are applying that T is positive, or T is positivity preserving, let's say. Okay, so respects the order. So T is positivity preserving. Then we said that if we want to continue from here, linearity will be perfectly fine, but actually we need slightly less, because it will be enough to know that, for instance, if I apply to the first term, that 1 over q1 applied to ai1 can be written as equal to okay, maybe let me do this first. So the first thing that we need to do here, if we have linearity, everything is trivial. I'm not going to discuss it. The other observation is that we could do slightly less in the following sense, that we could write that this is T applied to 1q1 a1i plus T applied to the other guy. So sorry, but I was kind of skipping a step, which is important, so I repeat it. So T1 over qm ami. Okay, so what is this property? This property is called sub-additivity. Okay, so that if I have an operation applied to a plus b, this is less than operation applied to a plus operation applied to b. So, and I applied it here m times. So then let us keep it here, T sub-additive. And finally, we would like this to be able to take the 1 over q, to take it outside. Okay, and in order for this to be true, we need positive homogeneity. So T positively homogeneous. Okay, so and in that case, we would have that this is 1 Q1 TA1 plus 1 over Q2 TA2I. Well, I should say apply to the whole sequence, right? So I should put parentheses here, but I just don't want the notation to become too heavy. TA. So what we used before was when the operation T was a sum. But then do you know other operations that are positivity preserving, subadditive, and positively homogeneous? Well, certainly, for instance, the integral, right? So nobody forbids to say that we can start from an inequality instead of having I, we have X, let's say, if you prefer this notation, but this is just a dummy, so it is not really important. And from this pointwise inequality, we obtain for free the Hölder's inequality for integrals, right? Because it is just the observation that there is nothing special about summing. It is exactly the same if I apply any operation T which has these three properties. Because these are all just algebraic operations that I'm doing. I'm not doing any, there is no analysis involved here. It is purely algebraic operation. Okay, so then what is the form of this expression then? Well, it will just be if we apply the integral, if we should apply it to, by the way, why didn't you tell me that I forgot the exponents here? So there are exponents involved here. I left them out everywhere. QM, Okay, so if we applied the integral as I just said, we obtain that the sum of AIAM is less or equal than 1 over Q1 integral of A1, where A1 now is I treat it as a function, okay? A1 Q1 integral, it is, we can just think of the Riemann integral as always, because I'm not assuming explicitly that you know about the Lebesgue integral, so there is no need for that. So AM to the power QM, okay? So as usual, we said that when we do this type of examples with integral, we take a compact interval on the real line, and that is enough. And you see that the argument is exactly the same, because this will be less or equal than the sum of the Q1. Sorry, I wrote here in sum, but it was an integral, and Qm, and again this is equal to 1. Okay, and of course, if you are afraid of this type of argument, just replace AI by AI hat, and defined as AI over, so the function AI. So if you want, I put the argument here in order to make it more explicit, and you write here AI to the power QIX to the power 1 over QI. Okay, so it is exactly the same that we have done before. So it is actually interesting to make this observation about the possibility of applying these algebraic operations T, because by the way, we could also further, let's say, this type of observation by saying that we don't even need this operation to take values in R. It could simply take values in some set in which we have a notion of order. Okay, So this is particularly important. Well, at least it was particularly important for the original plan that I made of this class, but I am now not very optimistic that we will be able to do everything I wanted to do. But anyway, so this is already a very interesting fact. As always in our discussions, we tried to identify the case of identity, and this is something that we have not done yet. So for this, we restrict to the case where we have only two functions. So maybe now, well, I will keep calling also if they are functional, we'll keep calling them I hope you don't mind, even if maybe you're used to seeing F instead of I, but it doesn't play really any role. The claim is the following, that if I have two functions, A and B, so that I integrate A and B, and if I have equality, I have this chain of equalities. Okay, we need to introduce another norm that I will, another notation for the time being. We don't know whether it is a norm. Later we will prove it. So now I will just use this subscript P and P prime. So first, a little piece of notation is that whenever there are only two exponents involved in the Hölder's inequality, instead of writing P1, P2, people usually write P and P prime or P and Q, whatever. I prefer this because it keeps track of what it is. And of course, this is nothing else than asking that 1 over P plus 1 over P prime is equal to 1. And also, when A is a function, we use this notation. As usual for us, A are well-behaved functions in order that we can integrate, we can take the Riemann integral without any problem and so on, okay? So this is A to the power P, 1 over P. So essentially we replaced the summation sign by the integration sign, okay? For us, I repeat, it is for the time being only notation because we don't know that it is a norm. After we have proved, we have discussed this case of equality, we will actually prove that indeed these are norms, and this follows by another one of the fundamental inequalities that we discuss. Okay, so the claim is that we have this set of equalities if and only if either f is equal to 0 or g is equal to 0. So either we have this condition, but which is the non-interesting one, or, and this is the more interesting one, there exists lambda real such that we can write that B is equal to lambda sine of A P minus 1. This is just, so this should be interpreted simply as pointwise, okay? So B of x equal lambda sine of AX, so I don't write the x all the time. When we have this type of expression, it always means, for function, they mean pointwise. Okay, so the proof is not difficult, but it is not entirely trivial. So let us see the proof of this. So as a matter of fact, there is direction which is quite easy, and I would leave this to you. So this direction is very easy. So if we know that there exists a lambda that does this, then proving that we have equality here is something that is just reduced to computation. Okay, so I would leave this to you as a very simple verification. In order to prove, so this is exercise. Let us instead prove this condition, which is the necessary condition for equality, which is more interesting. The proof is more interesting. So the first observation is the following, that if you have that the integral of AB absolute value is equal to the integral of AB, then this implies that the sine of alpha of A multiplied by the sine of B is actually a constant. So is a constant that I call alpha. Again, I would suggest that you prove this by as an in a relatively easy exercise. So the idea is very simple. So since here we have equality, there are only two possibilities: either that that the integral of AB is positive, or that the integral, but with the same absolute value of the left hand side, or that AB is negative with the same absolute value of the right hand side. So then, if you make the assumption by contradiction that there are regions where the sine of A and the sine of B multiply in such a way that alpha is not constant, then you will find a contradiction to this identity. Okay, so assume that there is an open set, so that that if you integrate the Riemann, if you integrate one in the Riemann sense, the constant function one in the Riemann sense over that open set, then this is strictly positive. Suppose that there exists an open set where you have that this sign is different from the sign somewhere else, and construct a contradiction, construct a counterexample to the identity. Okay, so you will see that this implies this fact. So it is simple, but not, as I said, this is probably the key to the observation, which is combined with the next key observation, which is the fact that if now we look at identity of equality between Fg and sorry, I used A and B, not Fg. So integral AB equal norm of A P norm of B P prime. Then if we go back and trace where this comes from the AMGM inequality, and this is possible if and only if we have this equal to A P over P plus B P prime over P prime. Remember that the AMGM in fact was formulated in a different form. Well, we had alpha 1 over P and beta 1 over P prime. Okay, so but it is exactly the same. I make this observation because then when do we have equality here? So don't make the mistake of saying we have inequality if A is equal to B. Actually, no, because the equality is if A to the power P is equal to B to the power P prime. This is due to the fact that we have to convert it to its canonical form, okay? If you don't mind, I don't do this observation here, this calculation explicitly. So, but then here we have equality, as I just said, if and only if A to the power P is equal to B to the power P prime. And if you do the computation, or in other words, you simply take the power 1 over P prime on both sides, this is equivalent to B being equal to A to the power P minus 1. Okay. At this point, we are not yet done because we need to, we really want to identify B, not the absolute value of B. So, and the way to do this is to just write this as B sine of B equal A to the power P minus 1. And remember that we had that alpha sine of A sine of B. We said that it is a constant. So we would like to bring it into play. And so a possibility is to multiply both sides by sine of A, right? So we would have B sine of A sine of B equals sine of A P minus 1. Now we notice that this is equal to alpha. Alpha, of course, is either 1 or minus 1. Therefore, we can just bring it here is 1 over alpha, and we have found that B is equal to a constant multiplied by this. Okay? We did this again under the assumption that we have already done the normalization, right? If we have not, if we do not have the normalization, then we would have this argument not for B, but for B hat, and we revert to the case B and A just by eliminating the normalizations. Okay, so I think this is fairly trivial. This is something that you can do by yourself. So in other words, I repeat, if we have this, we have also this, the sign of A and the sign of A hat are the same. Then you write explicitly what B hat is and what A hat is in terms of A, and you obtain exactly the same with the constant that will involve the norms of A and the norms of A and B. Okay, so this is the proof of the equality case in the Hölder's inequality. The proof with very minor adjustment continues to hold if you assume that A and B are functions with complex values. And the only difference is that you have to introduce instead of having that sine A sine B is constant, you need to take the complex, the imaginary argument, and to play with it a little bit. But the idea is essentially the same. As I said at the beginning, I will just mention what happens in the complex case, but I won't carry out the arguments entirely. Now that we have this, we show, and this is probably the first example that I give, where we show that having a characterization of equality sometimes is very useful, and we prove it in this corollary. So it is actually a corollary of, let's say, corollary of equality case in Hölder. And this goes also under the name of, well, this goes under the name of quasi-linearization, but I don't suggest you to remember it. It's not really important. So let P be a number between 1 and infinity. And then we claim the following. I'm not extremely precise about the hypothesis that I'm putting on the functions, but essentially all you need is that the integrals that we are defining are well posed, so they are defined. They don't need to be finite, but they need to be meaningful at least. So if you happen to have already seen the Lebesgue integral, you use the notions of Lebesgue integrability. If not, if you only have seen the Riemann one, take this with a little bit of let's say suspicion, in the sense that the calculations, if we only consider the Riemann integral, are slightly formal only. Okay. In any case, the claim is the following: that if we take a function f and we want to find the P norm can be written as the supremum of the integral of fg. Written like this. Actually, you can also not. You can also avoid the absolute value, but okay, I write it as a custom. Let's say GQ less or equal to 1. So this means that you take the sup of this absolute value of the integral of f and g with respect to all g, such that they're, say, I cannot yet call it norm, but this expression, let's say I call it norm with anticipation, with Q norm is less or equal than 1. And by something that you won't absolutely find surprising, we can also take the absolute value inside the integral, and the supremum will be taken on exactly the same set. Okay, and if we want to prove this, you see that there is one part of the argument that doesn't need absolutely any proof, I believe. Oh, by the way, it would have been better if I had written it. Okay, it would have been better if I had switched this to parts, because you see that that this is larger or equal than this part comes exactly from the Hölder's inequality, correct? So maybe we write it. Let us write. If we have fg, then we have the following, right? We have fg less or equal than integral of f of g. So this is a property of the Riemann or the Lebesgue integral always. So this doesn't need a proof. And now we apply the Hölder's inequality, which says that this will be less or equal than f p g q. Well, okay, I should have written p prime, sorry. Let me write p prime then. P prime. P. Okay, remember that again we use this notation. Okay, but if we take the supremum over all the function g such that this gp prime is less than 1, then clearly we just have that the supremum on this side, supremum on this side, and we take supremum here, this can be eliminated, right? So we have proved that this is less than this is less than this. So we only then need to prove the other implication, but but the other implication is proved simply if we exhibit a G which attains the supremum, right? But this is exactly, it is pretty much the same that we have done in the previous step. So maybe I just briefly repeat what we got. We started taking a function g, sine of f, and then you take f to the p minus 1. So this is not necessarily normalized to 1. And then from this, you produce another one, which is normalized to having p prime norm equal to 1. And you don't need much time to convince yourself that this will be obtained just by doing g 1 over f p minus 1 sine of f, and then you take f p minus 1. Okay, so if you do the computations yourself, you will see that starting from this guess, which comes from the equality case, we produce a function g which has p prime norm actually equal to 1, which attains the supremum. Okay, and this completes the proof. This is actually a very useful way to check or to find estimates on the pth norm of a function. Now it's time to justify this abusive terminology that we have used so far, and to prove that indeed this definition provides a norm. So we want to prove. That this notation that we have just used as notation up to now is indeed the norm. We want to prove this, and the answer comes from a very famous inequality, which is the Minkowski's inequality. Which says the following. It says that f plus g p is less or equal than fp plus gp. So it establishes the triangle inequality for this function, which, well, you see that homogeneity is trivial, and the fact that the only, at least if we restrict to the continuous function, the only continuous function whose pth norm is equal to 0 is the 0 function. Okay, so it is indeed a norm. If you want to, if you have already seen the Lebesgue integral, things are not so simple, because you need to look at functions that are 0 quasi everywhere, almost everywhere, and so on. So, but we don't discuss that. Okay. So, is it always the case for all p? No, the answer is no. But we need the same restriction that we had for the that I indicated, at least for the little LP spaces. By the way, I use this notation, but you will see that by an argument entirely similar to the one that we have given before, right after discussing the Hölder's inequality, since we will obtain this inequality by integrating a pointwise inequality, this will remain true for a much larger family of operations, of algebraic operations that satisfy those properties that we said before. So positivity preserving, positive homogeneity, and subadditivity. In other words, it doesn't matter whether we integrate or we sum, because both integration and summation are examples of those operations, and we will get in one shot both the inequality for, in the sense of this norm defined on integral, as well as for series or sequences. So let us see. The application, the first proof is actually really a simple application of the Hölder's inequality, which goes as follows. So we just write f plus g to the power p. We write it as f plus g, and then f plus g to the power p minus 1. And here we use only, so this is this is a pointwise identity, and we continue with pointwise operations. Okay, so this, I use the triangle inequality on the real line, so there is nothing new here. Then at this point, I make the observation that now I can integrate. I split this integral in two terms, and for the first term I have f, and then f plus g p minus 1. Now I make an observation that, of course, I would like to extract the power p from here. So I need the exponent p, and I need its conjugate. Okay, I need the conjugate exponent p prime equal 1. Then I compute what p prime is. And you will see that p prime is nothing else than, and this please do it yourself, it is p over p minus 1. So this will be bounded by the integral of f to the power p, 1 over p, and the integral of f plus g to the power p minus 1 times p over p minus 1, and then here over 1 over p1, which is p minus 1 over p. In other words, then of course we have also the same inequality when you have the g. So f of g, this is symmetric, so we have the same inequality. We end up with f plus g pp. Okay, so notice that this is what we are trying to prove, it is a norm. So this norm to the power p, and then we have less or equal, then what is this guy? This is f to the power p, and then we have f plus g. Now let us read. So this is p 1 over p to the power p minus 1. So this is p minus 1, right? So power p, power 1 over p is f plus g norm p. And then we have an exponent p minus 1 that I put here. And we have exactly the same term, but with a g that I write here. sorry, the P was downstairs. Okay, so we have this first part multiplied by this, and then you see immediately that all we have to do is to take f plus g p minus 1 and to divide by 1, to divide by it on both sides. If we divide by it on both sides, this disappears, and we are left with exactly the Minkowski's inequality. Okay, so this is the proof. You get exactly the same inequality if instead of applying the integral, you apply any operation with the property that we discussed before. So in particular, consequences that this LP is a norm, and also this definition of LP is a norm. So normally, I don't want to use the notation LP, but so capital LP, but that is related to that. I'm not using that notation because it requires arguments from measure theory that I don't want to use at this level. Okay, good. So as usual, I'm not very far ahead in what I wanted to show today, but we still have enough time, and I hope I managed to do something. Okay, the next thing that I wanted to discuss is at least the very beginnings of inequality coming from convexity. And we will recover, actually, we will see that convexity in a sense is a unifying tool for many, essentially all of the inequalities that we have seen so far. So let us recall that I need to go a little bit faster here. I hope you don't mind. That if we have a vector space E, so E vector space, and C a subset of E, then we say that C is convex if x, y in C implies that lambda x plus 1 minus lambda y is in C for all lambda belonging to 0, 1. This is exactly the same as saying that if you have a set, the whole segment joining x and y belongs to the set C. And I hope that you have seen convexity already in some undergraduate courses. And I would suggest you to check that this is true if and only if. So this definition of convexity can be slightly extended to the following formulation, that x1 up to xn in C and lambda 1, lambda n positive numbers summing up to 1 implies that the sum of lambda I xi belongs to C. Okay, so this sum is often called the convex hull of the points x1, xn. So this could be expressed saying that a set is convex if it coincides with its own convex hull. Okay, this sounds like a tautology, but it isn't. So this claim needs a proof. The proof is not hard, but I suggest you to check that this is correct if you have not seen it before. Strictly connected with the notion of convex set is the notion of a convex function. So if we have a function f from C to R, where C now is this convex subset of a vector space, so I should have said the vector space on R, so on the field R, then we have the following, that the function f, by definition, the function f is convex if the following happens, that f lambda x plus 1 minus lambda y is less or equal than lambda f of x plus 1 minus lambda f of y. And this is also extendable in a very similar way as we claimed in the definition of convexity. And I ask you to check, although this will be explicitly written in the lecture notes, that if we have this same situation here, then we have that f of lambda 1 x1 plus lambda n xn, this is less or equal than the sum of lambda I f of xi. And this characterization of convexity is often called Jensen's inequality. At least it is the simplest form of the Jensen inequality. Okay. So this Jensen inequality, as a matter of fact, looks almost innocuous, like a very almost a trivial not generalization, but let's say characterization of convexity. But as a matter of fact, it is very powerful in spite of its simplicity. And as a first example of its power, I guess it's also going to be the last, given that it is so late. But I will give yet another proof of the AM GM inequality. And you will see that this is probably in terms of being self-contained and quick and so on, this is probably the best of all proofs that we've seen so far. But still, it requires a little bit of calculus, but very, very basic one. Much more basic than the calculus needed in previous proofs. A part of the almost purely algebraic proof that we gave at the beginning, which was nonetheless not particularly quick. So remember that we are after a bound for this quantity. And so we will write this as, so a1 to the power p1 can be written as exponential of p1 log a1, and the same can be done for all of the other terms. So of course this can be written just as exponential of let's say I will write p1 log 1, all of them, pn log a. Now we have to remember, I definitely hope that this has been seen before. So now we use the fact that the function xe of x is convex. So this implies, by the characterization of convexity, or if you like, by the first form of the Jensen's inequality, that this is less or equal than p1 exponential of log a1 plus pn exponential of log an. And of course, you see that this is nothing else than pa1 plus pnan, which establishes the AM-GM inequality. Okay, so this is extremely quick proof of it. I would maybe, as one last thing, that yes, if you allow me, maybe I take another 3-4 minutes, and I would at least mention what the statement of a relatively general form of the Jensen's inequality is. So as I mentioned yesterday, however, the proof is not really trivial. So let f be a continuous function. So continuous and convex function on R. Okay. As a matter of fact, it will be enough to have on an interval, on interval C, if we want to have, remember that we had this notion that whenever we write 1d mu, this means that we have a weight given by the function mu. So this is mu x dx. Okay, so this is integral of the function mu x dx. This is done only because I want to remain in the setting of the Riemann integral. So assume that we have this condition, or C could be the whole R. It is not important, as this is the important condition. Then we would have the following, that assuming that all integrals are well defined, that if I take any function f and I do this integral, then this is less or equal than the integral of f d mu. Okay, so how do we prove this? I just give one line argument appealing to a theorem that I'm not going to prove. And the proof is the following, that if the function f is convex and continuous, we can write that this is the supremum of aix plus ci, where ai and ci are real numbers. Okay, so pointwise for each x, we can write this thing here. And then the idea is just the following, is just to write pointwise the inequality aif plus ci, to take the integral on both sides, and then to take the supremum to recover the f. So this identity is not trivial at all. The rest is essentially a triviality. Okay, so I have left only 5 minutes, but I hope this is okay, and I stop here then. Maybe let me just mention that I will add much more complete explanations in the lecture notes with respect to what I mentioned today. Okay.